Hi, good morning. So, this lecture is about a concept called a voltage standing wave ratio, which, it comes from the fact. So, this is a figure of merit for figure of merit for how well something is terminated. So, um, and so I'll talk a little bit about that, about why this is a figure of merit, why is it used, and how does it relate to the fact that we have a standing wave in a transmission line. So, what we've talked about so far about transmission lines has been, let's say you have a transmission line and it's terminated in some way and it has a certain impedance, let's say it has a certain source. But just as easily, you could have the same kind of a situation. You have a transmission line, and let's say for some reason you have an amplifier at this point in the transmission line that then sort of drives another transmission line. Let's say you want to have a gain of your signal coming in here. So let me see if I can do this. I had pulled up. So here's a spec sheet for a low noise amplifier that I just picked from the web. So it's an amplifier you'd use for this kind of purpose. Notice it's got a coaxial input, coaxial output, but so it's made for these kind of transmission line circuits. It's high frequency. You guys can see up here it's zero point 0.4 to 3 gigahertz, etc. And it says it's a 50 ohm. It says 50 ohm up here on the top left. You guys probably can't see. I can't point to it, or you won't see any way for me to highlight it. But it's up on the top left. It says 50 ohm. So that means they've tried to 50 ohm input terminate and 50 ohm output terminate the amplifier. So if you have a 50 ohm characteristic impedance transmission line going to this amplifier, it should be perfectly well terminated. So as you can imagine, the real world isn't perfect. So this 50 ohm termination with manufacturing tolerances and across frequencies, etc., may not always look like a 50 ohm termination. It might change in frequency, might because it's the input termination being what it is. So here in the specification table, notice they have two parameters. I'll focus on the input voltage standing wave ratio, VSWR. And basically what they're saying is they're using this parameter and it's a number between, let's see, it's saying this is at various frequencies and it ranges at different frequencies. It's around 1.9 and drops down to 1.8. And then the unit is it's just a ratio. So the unit, there's like unit less quantity. So today we're going to talk about what this means. It's basically a measurement of how good that 50 ohm input termination is. That input termination is not going to be exactly 50 ohm because there's manufacturing tolerances. There are there's it's that is made out of there's inductors at the input, there's capacitances at the input, and so on. So depending on the frequency, so this voltage standing wave ratio as a function of frequency. Depending on the frequency, that input is close to 50 ohms by a certain amount. And so that's what this voltage standing wave ratio means. So going back to, so that's kind of upshot of um, what we're going to be looking at. So let's look at the um, how we get there. Okay, so as we saw, as long as you don't have perfectly well terminated transmission lines, you're going to have a standing wave in your transmission line. Okay, what does that mean? It means that if you have a transmission line with a characteristic impedance Z0, and then you have a load impedance, and let's say Z0 isn't exactly Z sub L, then you're going to have a standing wave in your transmission line because you're going to get reflections. You're going to get a transmitted wave, then you're going to get a reflected wave, and the reflected wave and the transmission wave are going to be constantly interfering with each other. The sum of those two will set up an interference pattern in the transmission line, and that'll have maxes and mins. We already talked about that a little bit, but let's kind of visit it again. Okay, so if we take slices of the transmission line, look at this transmission line at different points along its length. If we take any point along that, and if we measure the voltage at any of these points, we can't measure just the forward going voltage or just the reverse going voltage because they're always lying on top of each other. So measuring the voltage at any of these points, measuring voltage, what you're measuring is the sum of V0 plus and V0 minus, including their phases and that variation across the transmission line. Okay, and by looking at the we're again sort of giving you guys the punchline by looking at the amplitude of this value along this transmission line, we can find out something about this load impedance. Okay, and the reason is, I'll repeat this a few times, in practice it's easy to talk about what load impedance is, but it's usually very difficult to directly measure this load impedance, especially at high frequency. It's not like you can put a multimeter across something and figure out what its impedance is, because multimeters are at very, very low frequencies, practically DC frequencies. So you can't use a multimeter, and that impedance also changes with frequency, and you're measuring it at multi-gigahertz. So in practice, you can't really measure the impedance directly, and people use this sort of standing wave, the amplitude of the ratio of the sum of the voltages along the line to figure out something about the load. Now let's look at how you could go about doing that. So let's say we have our transmission line with the load, characteristic Z0, and let's say this is direction Z, and the load is sitting at Z equal to 0. So the total voltage phasor, the function of Z, is the forward going wave plus the reverse going wave. The reverse going wave as you know, is just a reflection coefficient times the forward going wave. So if we plug this into here, we get for the total voltage V0, whoops, V0 plus e to the minus j beta z plus gamma sub L V0 plus e to the plus j beta z. In general, the reflection coefficient might be complex. There's no reason it won't be complex. There's no reason it won't be real or will be real. Sorry. So in general, it's going to be complex. So it might have a form of gamma sub L e to the j phi sub L, where this gives the amplitude of the complex value and gives the phase of the complex value. Okay, so if we plug that in for the phasor amplitude, we get V0 plus 1 plus gamma sub L e to the j 2 beta z plus phi sub L. So notice we pulled that V0 plus. There was a V0 plus here, a V0 plus here. We pulled it out. And then let me actually show you how it's done. Kind of took the steps before I so how to get here. I jumped too many steps. So let me tell you what we're doing here. So V of z is V0 plus e to the minus j beta z plus gamma sub L V0 plus e to the j beta z plus phi sub L. And so we can pull out V0 plus e to the minus j beta z out of both sides. And then we'll have gamma sub L. And now because I pulled out e to the minus j beta z from here, that gave me 1. But if I pull out e to the minus j beta z out of here, I'm going to end up with 2j beta z once I multiply that. So 2j beta z plus phi sub L. Sorry, parentheses. Let me clean this up here. E to the j e to the j beta z plus phi sub L. So e to the j 2 beta z plus phi sub L. Okay, so here and then we can expand this again, e to the minus j beta z 1 plus gamma sub L. We can expand the exponential in terms of cosine and sine through Euler's rule. So we end up with cosine of 2 beta z plus phi sub L plus j sine of 2 beta z plus phi sub L. Here's the parentheses. Okay, and then basically if you want to take the amplitude, we get kind of the amplitude of this whole thing, and we end up with square root of 1 squared plus gamma sub L squared cosine squared 2 beta z plus phi sub L plus 2j cosine of 2 beta z plus phi sub L times sine of 2 beta z plus phi sub L minus sine squared 2 beta z plus phi sub L. Okay, and after all that, we end up with v of z is equal to v0 plus 1 plus gamma sub L squared plus 2 times gamma sub L cosine 2 beta z plus phi sub L. And this whole thing's squared up. Okay. So after all that, okay, so let's see what this looks like, what this equation for. So just to after that whole mathematical function, just remembering what we were doing is we were calculating the total voltage along the transmission line, which is the sum of the forward going and the reverse going voltages. And we wanted to see what the absolute value of that voltage was a function of distance. Because, if you put if you can measure just the absolute value of the voltage in the along the line, and you end up with this equation. Okay, so this is the absolute value of the total voltage anywhere along this transmission line, depending on the load and the characteristic impedance, which are kind of wrapped up in this reflection coefficient. Okay, so now let's look at a few cases of what this looks like for different kinds of loads. So let's say we're looking at the case of at z equal to 0, where the load is. Okay, right there. So v at 0, at z equal to 0, is v0 plus 1 plus gamma sub L squared plus 2 times gamma sub L cosine of phi sub L. And then this whole thing to the 1/2. Basically what I did is I took this equation, plugged in z equal to 0. Okay, now suppose, sorry, this is, now suppose that we have, this is example 1, suppose the load impedance is an open circuit, meaning that the reflection coefficient in that case ends up being +1, and the absolute value of the reflection coefficient ends up being 1, and the phase of the reflection coefficient is 0. So that gives us v hat of 0, absolute value, is 2 times v0 plus. And that's expected because the load, we expect that if the load is, if you have an open circuit load, the voltage would double at the load, as we'd seen previously. Okay. Now, the second case would be, let's look at the case 2. So example to, let's say it's equal to, impedance, load impedance is 0 or short circuit. In that case, the reflection coefficient is -1, and the phase is 2 pi. Sorry, the phase is pi. That's what gives us the minus. So V at the absolute value of the total voltage on the line at the load is equal to 0 in that case. Okay, only at the load. But in this case, we have also, so this is just at the load. So at load, as you walk away, walk backwards from right to left from the load. And let's say you're measuring the voltage values at any point along the transmission line, backwards from the load. You'll see that you'll have, because you have a standing wave, because of the interference of the forward going and reverse going wave, you'll have maximums and minimums in the voltage amplitude. And we've seen that before. Okay, we did this by simulations and so on. So the maximums occur because of the sine and cosines. Maximums occur at 2 beta, wherever the maximum, the location of the maximums are, plus phi sub L. Whenever this holds, you get a maximum, okay, whenever this equation holds, okay? And the minimums occur at 2 beta sine, 2 beta z min plus phi sub L is 2n plus 1 pi. So there's minimum and maximum. And the voltage of the maximums is V0 plus times 1 plus gamma L. And the voltage at the minimums is V0 plus. So at these locations, these are the voltages you would expect. So at the locations of where the maximums happen, you expect this to be the value, and where the minimums happen, you expect this to be the value of the voltage. Okay, so now we define this new thing called a voltage standing wave ratio, or VSWR. And we're defining that to be Vmax over Vmin. So the ratio of what the maximum voltage values are to the minimum voltage values. So, um, and then this ends up being, because of that ratio, because of this equation, it ends up being 1 plus gamma sub L over 1 minus gamma sub L. So we know the absolute value gamma sub L can only be between 0 and 1. So if you know that, the range of standing wave ratio can be between 1 and 0. Sorry, 1 and infinity. Sorry. So, meaning that if the reflection coefficient is 0, meaning that you're perfectly well matched, so there's no mismatch in the load, your voltage standing wave ratio is going to be 1. So it means that the max voltage and the min voltage of your standing wave are the same, and you really have no standing wave. So if you're looking at the voltages, if you're perfectly well matched, you won't see a standing wave. There's no maximum and minima because the voltages of the maximum and minima are going to be the same. Um, there's no standing wave in this case. In every other case, you end up with a case where whenever you have a voltage standing wave ratio higher than a value of 1 is you have a case when you're not perfectly well matched, meaning that there is this absolute value of gamma sub L is something other than 0, means that you do have a ratio between V max and V min. So the more mismatched you are between the load impedance and the characteristic impedance, that ratio between the Vmax and Vmin will be higher, and in fact, it could be very large. But that ratio, so this value voltage standing wave ratio, tells you kind of how mismatched you are between the characteristic impedance and the load. So again, the reason this becomes really useful is because in practice, it's very difficult to measure the load characteristic impedance directly at all these high frequencies, etc. So what people do to get a measure of the load impedance is to put it on a transmission line. So you basically put your load on like a known impedance transmission line, and you go through your transmission line with essentially with the power RF power meter, and you measure the voltages along your um, along your transmission line, and you find your maximum. You'll see a maximum value, and you'll see a minimum value, and you'll see again a maximum value, and then you walk again, you'll see a minimum value. So these are just standing waves, so all you have to do is, you can just sort of like, you have just a power meter. You don't need to worry about frequency, etc. It's a standing wave. And basically using that ratio, you can figure out your load impedance. And then the value of V max over V min, the absolute value, gives the absolute value of the reflection coefficient, and the location of Vmax and Vmin gives the phase information for your complex reflection coefficient. So by basically walking through your transmission line with a power meter, looking at the values of the standing wave, you can figure out what your load impedance is. So this is something that, like, as I showed you guys, like, again, where was I? Here we go. So this is something that the RF manufacturers also give you. Now, when you look at, you kind of see how we've plotted voltage standing wave ratio versus frequency here for the input. The red is the input. And basically, it's saying how well matched you are to 50 ohms. It was, if you guys remember, it was like 1.8, 1.9. So it's not 50 ohms exactly. And so you kind of like get what the what the values are. Okay, so generally, if the closer you are, so if if you have a situation, so if um, voltage standing wave ratio is closer, the closer it is to one, the better matched it is. Okay, and it just really depends. I mean, how badly. I guess you're never gonna get really one, but you know, like one. I mean, it just depends on what your rule of thumb is. But I think you, I think in practice, you're gonna have voltage standing ratio between one and two, and it really comes down to how good of a job the manufacturer did to control that. Um, to control that. Okay, so let's look at a few examples of what you would actually see. Okay, so let's say you're measuring this. So look at a case of case A. Let's say you have a case where the reflection coefficient absolute value is zero, and that means that Z sub L is equal to Z zero. The voltage standing wave ratio in that case ends up being one. So V at zero hat amplitude is equal to V at zero plus R. Okay, so if you look through the transmission line, what you'll see is, basically you get the wave, forward going wave, traveling through the transmission line. But because you only have a single wave and no reflecting wave, you won't have a standing wave. And there'll be, if you're going through and holding your power meter here, at some point you'll get the max value, but soon after that, as this wave is traveling, you'll see the min value there and so on. So because the wave is fully traveling, there's no standing wave, you won't see any maxes or mins because you only have a forward going wave, no standing wave, and so we won't get maxes and mins. Okay. Now let's say you get a case of, so case B is, let's say the reflection coefficient is plus one and the phase of the reflection coefficient is zero, so that means you have an open circuit. So open circuit is P sub L equal to zero, short circuit is P sub L is equal to one. So in this case, the voltage standing wave ratio is infinite. That means if you walk back along your transmission lines, why is it infinite? It's the ratio between the highs and the lows, and it's infinite because the lows will be zero and the highs will be some value. Okay, so and so if you just look at the forward open circuit, we'll have V sub Z absolute value is V0 plus 1 plus gamma sub L squared plus 2 times gamma sub L cosine 2 beta Z plus phi sub L, the whole thing to the 1/2. These will be 1, 1, and so you end up with V0 plus 2 plus 2 cosine of 2 beta Z to the 1/2. So the maximums occur at 2 beta Z is equal to 2 pi m. that means that basically as you walk back from z equal to 0, you're going to see, this is for the open circuit, you're going to see, of course, your first maximum you're going to see at the load. The first minimum you're going to see at sort of this point, which corresponds to lambda over 4, the wavelength divided by 4. And then if you have a short circuit, what you're going to see is 0 at the load. And you're going to see the first maximum at lambda over 4 and the minimum at lambda over 2. So, okay, now let's look at a case of, let's say it's some intermediate case. So assume the z sub L is going to be j z sub 0. So a purely inductive load. Okay, so in that case, gamma sub L is equal to 1. Standing wave ratio is infinite. So V max over V min is some finite value over 0, which gives you infinite. And phi sub L is equal to pi over 2. And you're going to have these values of 2 pi z max plus pi over 2 is 2 n pi. And that says that the maximums will happen at minus lambda over 8. And since lambda is the phase velocity over the frequency, z maxes will be minus the phase velocity over 8f. The minus is because you're walking from right to left, so you're kind of going in negative z direction. So it's away from the load. Okay. And so let's say you have this purely inductive load. Basically, you can kind of walk backwards from this and figure out by looking at the standing wave ratio, figure out what the load impedance is. And so there's a graphical, very famous graphical way of doing this. So there's a graphical way of looking at this called the Smith chart, which we'll be covering in a little bit. And that's used to basically look at what happens as you walk away from this